Okay, we're now going to, in this lecture, talk about series of real numbers. We've already talked about them a bit with the harmonic series, but now we're going to talk, going to be a bit more precise in our discussion. We'll start with some definitions. First, let Sn, and note it's a little s, be a sequence of numbers. We will refer to capital Sn equal to S1 plus S2 plus S3 plus ... as a series. Okay. Embedded within this nomenclature is an understanding of an associated sequence, capital Sn, of partial sums of S defined by Sn is equal to the sum of little s1 through little sn. We will say that a series S converges if the sequence of partial sums Sn converges. In the case it does, we will abuse notation by referring to the value of the limit, the target value of the series, by the name of the series itself. That is to say that the limit as n goes to infinity of capital S sub n is equal to capital S. So two examples that I want to talk about in this lecture, one of which is a geometric series of ratio 1/2, and this is g is equal to 1 plus 1/2 plus 1/4, and each time we cut the value of the term in half. The second is the alternating harmonic series, where we take the terms of the harmonic series and alternate putting plus and minus between them. Okay, so what are we going to do with these? Well, first, we're going to prove that the geometric series converges. Okay, in fact, that this geometric series with ratio 1/2 converges to 2. Okay, so let's start off with a little algebraic formula. Recall that 1 minus x to the n plus 1 is equal to 1 minus x times 1 plus x squared up through x to the n. If you don't believe me, you can just carry out the multiplication. It works, okay? And so given that, we can solve for 1 plus x squared up to x to the n, so that this sum of 1 plus x squared up to x to the n is equal to the ratio of 1 minus x to the n plus 1 divided by 1 minus x. Okay. Now, if we let x be equal to 1/2, this left-hand side becomes the nth partial sum of our geometric series g. So it's equal to gn. And so we have a formula for gn, which is 1 minus 1/2 to the n plus first power divided by 1 minus 1/2. And now this is misleading, okay, in terms of the rest of the series. There are extremely few series that have a formula that's nice associated with their partial sums. So just stop looking now. Okay. We use these special cases where this works, but we finesse them. Okay. So what about this gn? We've got the formula for partial sum. Well, we write it in a little different formula, do a little algebra to it, and so it's 2 times 1 minus 1/2 to the 2nth, and we then, let's calculate the limit. Use the theory we've developed. This limit in between the big parentheses goes to 1, so it's the limit of our partial sums is 2, and therefore the limit of our series is 2. Okay, now we talk about the alternating harmonic series, it converges. Even though the harmonic series diverges, the alternating harmonic series converges. So the series A minus is equal to 1 minus 1/2 plus 1/3 minus 1/4. Okay. It will converge. And here, okay, we don't tell you what it converges to. In fact, it'll be a while before we figure that out. Okay, not this lecture certainly. I might tell you what it is, but we will prove that it converges without proving what it converges to necessarily. So note that A1 is equal to 1, and our first partial sum. Our second partial sum is 1/2, and so A2 is less than A1. Also note that A3 is equal to A2 plus 1/3, which is 5/6, and A4 is equal to A3 minus 1/4, which is 7/12, and so A2 is less than A4 is less than A3 is less than A1. But this is suggesting something. You know, the A2, A1 form a closed interval. The A4, A3 form a closed interval. And so what we have here is the suggestion we might have a decreasing sequence of intervals. Okay. And so let's check. Okay, we take we take the difference of the partial sums that are even. Okay, and so they're positive. We take the difference of the partial sums that are odd. In this order, they're negative. And so we note that A2n minus sub 1 minus A2n is equal to 1 over 2n plus 1, and that's positive. And so combining all these, we get that A2n is less than A2n plus 2, is less than A2n plus 1, is less than A2n minus 1. And so we do have this nesting of our intervals. Okay. Now the length of A2n plus 2, A2n plus 1 is 1/2, and it is 1 over 2 to the n plus 2. And so actually this should probably not be here. Okay. But in any case, what we see is the length of the intervals is becoming arbitrarily small. Okay, let me take a look back here. Okay, that's fine. I did it right. Never mind. And so the length of our intervals is getting arbitrarily small. And so by the nested interval principle, there is a unique number that is common to all of these intervals. And our series of partial sums will converge to that value. Again, let epsilon greater than 0 be given. Choose an n so that if little n is bigger than capital N, then 1 over 2n plus 1 is less than epsilon. And suppose that little n is bigger than 2n plus 1. Then an is in this interval a2n plus 2, a2n plus 1. Therefore, an minus c is less than epsilon. It follows that an, our sequence of partial sums, converges to c, and so the alternating harmonic series is convergent. And we can, in fact, get an error estimate how close it is to the limit. Our an is within 1 over n of the limit. It doesn't converge very fast, but it does converge.